A colleague of mine claims that the mean weight for adult Labrador retrievers is at most 60 pounds. So 60 pounds is included in this or something less. So my null hypothesis ends up being mu less than or equal to 60 pounds. This is my dog Penny saying hello, and just out of curiosity, she actually does weigh 60 pounds. But I don't want to let my dog speak for the entire population of adult Labradors. So what I do is I go and collect a sample of 12 other Labrador retrievers, and I compute a sample mean of 79.3 pounds and a sample standard deviation of 15 pounds. So remember, this is information I'm getting from the actual population, right? I have 12 dogs. I compute their sample mean weight and their sample standard deviation of their weights. Right? Okay, so innocent until proven guilty. We're going to assume that my colleague's claim is true. We're going to assume that mu is less than or equal to 60. Now we're in the background, we're trying to disprove this, right? So let's give the most credence to our colleague and say that mu is actually equal to 60. We're still going to show that this is false using our sample data. That's the hope. Now, under that assumption that the population mean is 60, as we've seen in the past week, we can say something about what would happen to a distribution of sample means that would come from a population where the true mean was equal to 60. Assuming that H0 is true, central limit theorem, or something kind of similar, essentially tells us that what we end up with as a distribution for sample means is a nice bell-shaped curve where the peak occurs at our null hypothesis claimed value. So our peak here would be at 60 pounds. Now, what we're going to do is go out and grab some actual data. We go out into the actual population of adult Labrador retrievers. We look at 12 dogs. We get a sample mean of 79.3. Now, what we want to do here is figure out, is 79.3 far enough away from where the usual values or usual sample means would be under the null hypothesis assumption? So this is our actual data. This is observed. We want to figure out what is the probability of observing a mean weight like this under the assumption that our null hypothesis is true. And we're going to tack onto this, what's the probability of observing a mean weight like this or something more extreme? Well, now that we're looking for probabilities, we need a probability model. We need some sort of distribution. And as we saw with our confidence interval work, when we're working with means and we don't know the population standard deviation, the best choice as a probability model ends up being a t-distribution. So what we're going to do is we're going to set up a t-distribution with 11 degrees of freedom. Remember, sample size minus 1 gives you the correct degrees of freedom. We now have a probability distribution. The peak of your sampling distribution goes to 0 if you convert everything down to t-scores. And what we finally need is a method of converting from our observed sample mean, the 79.3, down to this t-score axis, this t-distribution axis. All right, so what does 79.3 look like as a t-score? And thankfully, to some statisticians, we have a nice formula for how to take an observed sample mean with an observed standard deviation, compare it against a null hypothesis. So this mu here is 60. This mu is going to be the mean that we assume is true in the null hypothesis. And this should have sort of the flavor of a z-score computation, right? It's score minus mean over some sort of measure of variation. In this case, it's the observed sample mean minus the null hypothesis population mean divided by s over square root of n. This sort of feels central limit theorem-like. So hopefully that'll feel familiar to you. This s is our observed sample standard deviation, and we divide by square root of n because, again, we're dealing with a mean for a group, so we have this sort of central limit theorem correction in the variation of our x bars. Okay, so let's open up an Excel sheet. We'll compute this based on our data, and we'll see what t-score this ends up corresponding to. All right, so I took a couple of screenshots just so we have the pertinent information here. So fundamentally what we're trying to compute here is what we'll eventually call a test statistic, t hat. Remember, this is just the t-score version of our sample mean that we observed. So writing down some information here, x bar s n, x bar in this case was 79.3, s is 15 pounds, and our n was 12. And then we have mu at 60. And I'm just going to leave myself a note. This is from the null hypothesis. Right, that's what our mu value comes from. Now you'll notice there's two components inside of this formula, this t hat formula. The first is the top, which is just the difference of your sample mean from your null hypothesis mean. I'm actually going to break this into two pieces so that it's a little bit easier to compute, fewer parentheses. So the top is just going to be the difference of x bar from mu, right? So this is our observed sample mean minus what we're proposing as the population mean. And the difference there is about 19.3 pounds. Now, is that a big difference or a small difference? Well, it kind of depends on how much variation there is in the sampling distribution. And that's exactly what the bottom part, s over square root of n, computes. This gives us a sense of how much variation there is in the sampling distribution. So we'll take our sample standard deviation, divide by square root of n, and that's going to be in the bottom of our formula. Okay? So last but not least, we just take the top and divide it by the bottom, and this gives us a value for t hat. We can round this. Typically, you round to about 2 decimals when you're using tables. In our case, you don't have to round this, but this is just going to make things look a little bit easier. So essentially what this means, this is important, right? The sample mean of 79.3 pounds corresponds to a t-score of 4.46. And so in our picture, we can replace that double question mark with the actual t-score version of that sample mean. And now the nice part about this is since we know what probability model to use, and we know where our observed sample mean actually falls on this probability model, as a t-score of course, we can start to answer this question. What's the probability of observing our sample mean or something more extreme? So extreme means farther away from where the usual values are, which in this case is values that are bigger than 79.3. They're farther to the right, which is why we'll eventually call problems like this a right-tailed hypothesis test. So the equivalent question becomes, what's the probability of having a t-distribution score of 4.46 or something to the right, based on a degrees of freedom of 11, right? This comes from the sample size that we collected. So to compute the p-value, it's as simple as using a probability that a t-distribution has a score of 4.46 or more. Now, in Excel, let me zoom in a little bit. We've seen how to work with probabilities when we're dealing with the standard normal distribution or the normal distribution. It turns out we can do the same work with a t-distribution using a similar type of Excel function. Right? With confidence intervals, we use the t.inverse command to find critical values. To compute p-values for hypothesis tests about population means, we're going to use t.dist. So the way we would do this is first put it into cumulative form. Right? We use our familiar 1 minus trick. And then, rather than using like a norm.dist, we use the appropriate probability model. This is a t.dist. And it prompts us for 3 things. The first thing is the score itself, which in our case is the 4.46. Then we want degrees of freedom. Remember, this is n minus 1, which we can do in our head as 11. And then cumulative, we always set this to true. So this gives us an actual probability estimate for getting a t-score or something greater. So getting a t-score of 4.46 or something greater. Now look how small this probability is. 0.0005, essentially. Right? That's an exceedingly small probability, which is why we would say in this case, this p-value is so small, below many thresholds that you might want to set, that it provides evidence against the original null hypothesis claim. So in other words, we're going to reject the claim that the population mean weight for labs is 60 pounds or less. And that means we're actually providing through this data set evidence that the mean weight for adult labs is greater than 60 pounds. So we're siding with our alternative hypothesis.